All right, so today we're going to be going over the notion of higher order derivatives. And so basically the idea is we know how to find the derivative, right? So the derivative, let's say we have a function f, right? Function f. We know that the derivative of a function f prime, so f prime, gives us another function, right? Now, there's nothing stopping us from finding the derivative of f prime, right? Because f prime is just another function. And if it's differentiable, we can find the derivative of that function, right? And so the whole idea is finding the derivative of of a derivative is a higher order derivative. So the derivative of f prime will give us f double prime, that's the notation, or we can denote it as f with this sort of bracket 2, because let's say we have the 10th order derivative, right? We're not going to write out 10 of these little asterisks, or 10 of these little apostrophes, right? So this is the notation, and this just indicates this is the second derivative of the function f, or it's just the derivative of f prime, right? And why do we need these higher order derivatives, you might ask? So we know the whole notion of a derivative is, so the derivative is the tangent line of function f, right? Or the slope of the tangent line, the slope of the tangent line of function f at like its domain points, right? And the slope of the tangent line really just tells us something, which we'll cover later. This whole notion of the slope of the tangent line is really the instantaneous rate of change of that function, right? And knowing that slope tells us how that function is going to grow when we increase our x values. For example, if we knew that the slope, so if we had a function f, right, and we knew that f prime of 2 is equal to 4, we know that at point 2, whenever we graph f, we're going to have a positive slope, so our function f is growing positively, right? So that it really tells a lot about how function f is growing, right? And what if we had information about f double prime? Let's say f double prime was at 2 was -1, right? So that means that we know that at point 2, our function f is instantaneously growing at a rate of 4, right? That is our slope. But we also know that the rate of change of our rate of change function, so this is our rate of change function, its rate of change is -1. So the rate at which f is growing is getting smaller and smaller. So essentially what it means is as we go to maybe 3, f prime of 3 might be a little less than 4, right? Or might be around 3 or around a little less than 3. So it essentially means that since it still means that our function f is growing, but if our rate of change is becoming smaller and smaller, it might look like this, right? So essentially, the higher order derivatives tell us a lot about how the function behaves, and it tells us more information. And we'll see how later on we'll see the applications of higher order derivatives with respect to concavity and how functions grow. But the high level picture of higher order derivatives is it just tells us more information about how the function is and how its instantaneous rate of changes are. So let's just do a quick example of higher order functions. We don't really need to know the whole applications right now, but let's just know how to find higher order functions. So let's say we have a function y is equal to x to the power of 3 minus 5x squared plus 2, and the question is find all the derivatives of this function, right? And you might be wondering, aren't there infinitely many derivatives? But we'll see, like in this case, this statement of find all the derivatives kind of makes sense. Okay, so let's just start with our first derivative. So y prime, we know that is 3x squared minus 10x and then plus 0 because the derivative constant is just 0. So to find y double prime, we just find the derivative of y prime, which is just 6x. Now to find y triple prime, we just find the derivative of y double prime, which is 6. And then to find the fourth derivative, notice how I use this notation because writing out 4 apostrophes is kind of annoying. It's just 0. And then we know that any other derivative after, like if we have the 100th order derivative, it's just going to be 0 because the derivative of 0 is just 0, right? So that means we can stop at the first 4. And if we want to be complete, when a question is kind of ambiguous, like find all the derivatives, we can just say like from 4 all the way to like the infinite order derivative is just going to be 0. And so that's basically it, right? It's pretty simple. Finding higher order derivatives is just a lot of terminology, but it just means we continually find the derivative of our derivative function and keep going on. And later on, we'll see how the notion of higher order derivatives are, like, where are they applicable? And before I end, let me just go through all the different notation for higher order derivatives. So notation. So we already saw how we can use this double asterisk, or we can use this, or double apostrophe, or we can use number. If we want to use the dy over dx form, we can use d square y over dx squared. And this just also means the second derivative of the function y. And also occasionally you might see this. And that just means, again, the second derivative with respect to x, right? But since this is much more compact, you'll probably see this much more often than the one here. And that's basically it for